River-sea systems provide many ecosystem services that benefit us all. However, society has still found it necessary to interfere with the natural functioning of river-sea systems, either directly by enhancing specific benefits or indirectly due to pollution entering the water or atmosphere from agriculture, industry, or urban expansion. Whilst the benefits from these anthropogenic interventions may have been immediate, the complexity of these environments has often resulted in long-term negative impacts due to a lack of understanding between scientific disciplines across geographical and political boundaries. In this lecture, we use examples from the DANUBIUS-RI supersites to illustrate some of the impacts on river-sea systems. We start in the Danube Delta, where major engineering works in the 19th century designed to promote navigation have impacted the delta itself.
When we humans start to interfere with nature, we generate side effects we have no idea. Cutting the canal was extremely important because the waterways were shorter and definitely safer. At the Danube mouth, a series of jetties were built, initially about 1 kilometer offshore from the shoreline that was existing in 1860. We still have the relict lighthouses that show the position of the offshore part of the jetties. Then these jetties continue to be extended offshore up to the current length of 8 kilometers. Well, the idea was to take the sediments coming from the Danube farther offshore, but the work was somehow useless because the nature is definitely more complicated than the engineering level allowed back in the 19th century up to the first half of the 20th century. This is why continuous dredging was needed. And in the end, these two jetties that form the Sulina Canal allow a rather safety navigation waterway, but the costs to maintain it are definitely higher. And this is something that people didn't know back then. Building the Sulina jetties had also a significant role in changing the local circulation of waves and currents. A complete change in the coastal dynamics processes. To translate this, it means that the jetties generated a strong and rapid accumulation of sediments in one part, but they also generated a hugely intense coastal erosion. Why? Because the jetties did not allow to the sediments, to the sands that are the building blocks of the beaches, to be transported. So this is why instead of bringing sand to the beaches and support the accumulation of the beaches, the waves and currents started eroding, taking the sand from the beaches. And this is why we have these areas affected by the Sulina jetties, where we have had a historical erosion with a rate of 25 meters per year. It's one of the areas with the highest coastal erosion rates around the world.
The challenge of sediment management for navigation is also observed in Hamburg, where the dredging of sediment has led to unforeseen consequences in terms of biology, ecology, and water quality.
So we just entered the city limits of Hamburg. This is where Hamburg starts. On the right we have Blankenese, a nice small village. On the other side we have the premises of where Airbus is being made. What we see here, and you just filmed it, we had this big ship coming, leaving the harbor. And in order that these big ships can enter the harbor, the river has to be deepened up to a level of about 15 meters. And this is where the problem starts. is that in the Elbe River, which is very shallow, you have big phytoplankton blooms. They are nourished by all the nutrients, nitrogen, phosphorus, that are released especially through the agricultural practices. Now, the harbor has to be deep to accommodate for these big ships. And what happens is that the algae come from relatively shallow water into deep water. They can't grow anymore, but they are eaten away, they're being destroyed, and the organic matter that is then released is being degraded by microorganisms. Microorganisms need oxygen, and what you get, especially here in this part of the river, is an oxygen minimum zone. So why is this oxygen minimum zone such a problem? Well, one of the reasons is of course that a lot of fish are migrating from the sea into the freshwater zone. And if they have to pass an oxygen minimum zone, like is happening every few years, especially in summer, then they can't pass through the harbor and they can't go all the way up to the Elbe.
We have improved the status of the Elbe River and estuary over the past decades. We used to have eutrophication phenomena out in the Wadden Sea. That has improved a lot, but this eutrophication just moved upstream now, and we see its main effect in the form of oxygen minima, for example, in the harbor region today. So eventually, if we want to tackle eutrophication effectively, we need to reduce the nitrate load that is brought to the river, for example, by agriculture.
The need to facilitate navigation has also resulted in unforeseen impacts on the biology and ecology of the Danube Delta.
We have a canal that was cut to facilitate navigation along this branch of the Danube towards the Danube mouths, a canal that was cut 30 years ago. The canal was cut at a depth of about 8 meters, but the riverbed really self-eroded, so nature worked on itself and made a deeper slope so the Danube waters arrived faster, and now they arrive faster to the Black Sea. So the effect is that the natural meander is almost abandoned. It's similar to the arteries and veins that are clogged by cholesterol. So this is what happens, is less circulation and less water to the delta lakes means less oxygen, less food, and more stagnant water, and the result is death of nature. What's very important is to observe the color of the water. We are now in an area which is full of black water, and black water is the water of death. Why does it happen? Because humans in the 20th century mainly cut lots of canals, changing the natural circulation of waters and alluvia in the delta. And this is also an effect of climate change, of the heating up, growing temperatures. The water in these lakes, which are cut off from communication with the rest of the delta, so the water in these canals and lake gets hotter earlier, and the bacteria and algae in the water eat the oxygen in the water. They consume the oxygen in the water. So what happens is that the water has no oxygen, so it doesn't support life. Everything beneath it is dying, fish are migrating, only the dead organisms remain. So this is why we have this black water, which is really dangerous.
The biggest anthropogenic threat to our environment comes from climate change. Sea level rise is a direct consequence of climate change, which threatens low-lying areas around the world. Venice is no exception, and new countermeasures are being implemented to protect it.
The most important threat for the Venice Lagoon is the global sea level rise. It means that maybe in the next 100 years we will have 50 centimeters higher sea level, which means that at every single tide, twice a day, Venice would be flooded. And this is a big problem because people are still living in Venice, tourists are coming to Venice, and it will be a non-sustainable situation anymore.
We are here in an iconic place for Venice because this is the entrance of the city over the Sant'Andrea fortress. The fortress was built in this configuration in the mid of 16th century. At my shoulder there is the Bacino of San Marco and the basin, the starting of the lagoon. All the ships came into, for Venice, came through here and can be controlled by this entrance. These are the windows from where the weapons were put in order to defend the entrance of the city of Venice. The proportions are different. What today seems to be doors, actually they were windows, so the sea level actually reached the surface of the building more than 1 meter below. So this is a clear element where the subsidence and the relative sea level rise can be clearly seen. The sea level rise actually is not something so new for the city of Venice. But the builders, the ancient builders of the city centuries ago, would never expected to have a so big difference between the sea level of today and the sea level when the city was built. The point is that today we cannot destroy the cultural heritage of the past just to rise up the city even more. And so we have to maintain the present sea level, avoiding that flooding to the urban city.
So the problem of Venice is the high water, acqua alta, the storm surges, because when you have high sea level that is higher than 110 centimeters, the city gets flooded. And this creates a lot of problems, and therefore it has been decided to build these mobile barriers here now in order to be able to protect Venice from the high tides. These barriers, they're under the water. We have here a depth of about 12 meters. They are just lying on the floor, and when you need them, you put air into them, you bring them up, and then they will completely block the whole inlet here in a way that then no water can come in anymore from the outside sea into the lagoon. And this will help in stabilizing the sea level inside the lagoon and having the sea level always at a level lower than 100 centimeters, 110 centimeters.
By carefully characterizing river-sea systems, a combination of reinstating nature-based approaches in tandem with targeted engineering solutions and upstream monitoring can be effective in mitigating extreme events such as flooding. The River Tay, flowing through Perth in Scotland, provides a useful example of this approach.
So we've moved now down to the city of Perth, and the River Tay is now flowing behind me, as you can see. Under normal states of flow, the Tay has a typical discharge of around about 130 cubic meters per second. That's more than double, for example, the flow that you might see in the River Thames down in England. But even the River Tay experiences extreme events. So back in 1993, a peak river flow of over 2,260 cubic meters per second was recorded at Balathy, a gauging station upstream of where we are now. And that resulted in an extreme flood event, which is now marked in history in the wall of the bridge crossing the River Tay. That was actually beaten by a previous high flow of 1814, marked by the line just above me here. So during this flood banks were breached, and the resulting flood inundated many parts of Perth and the surrounding arable landscape, with destruction to ecosystem services and devastating social and economic consequences. Flood protection is critical to the future security of many towns and cities in and around river-sea systems. Perth is no exception to that, and although we've seen major schemes around many of the super sites that we have within the Danubius research infrastructure, Perth also has flood protection schemes. So here we have examples of floodgates which close during times of high water. So such barriers as these close before we have incidences of high flood within Perth. And these work in conjunction with an early warning system upstream of Perth, and also nature-based solutions where levees are being removed within the floodplain, and the floodplains are allowed to flood during times of high water flow upstream of Perth.
In London, we explore the risks associated with droughts and flooding, as well as climate change, and consider the mixture of engineered and nature-based solutions to manage these extreme events.
So from a general perspective, across Europe, water quality has improved enormously through implementation of the Water Framework Directive. We see that in the UK, we see that in Northern Europe, we see that in Eastern Europe. We have problems when there's too much rain in terms of how we can hold waters back to prevent flooding in London. There are problems when there's too little rain, problems of drought, whether that's winter drought affecting groundwater recharge, or summer droughts affecting the health of riparian communities. There are problems of poor water quality. And then to further complicate it, we have problems of changing sea level, relative sea level and absolute sea level. And we also have problems with changes in the way in which the catchment has been managed. And that might be changes in agricultural drainage upstream. It might be changes in the patterns of storm drainage that we see in cities like sort of London or Oxford or Reading upstream. It might be problems with extra water that's brought into the catchment through the water distribution system and passes out to the river through the sewage network.
Flooding is another key concern in the Thames catchment, and in particular floods occur commonly in the middle and lower parts of the system. These often occur in winter and through into spring. Now, as there are some key infrastructures and high-value properties and businesses along this river system, there are many engineered solutions in place to provide protection. If we go right down to the lower part of the system, to the estuary, we have the Thames Barrier, which protects London against flooding from the sea. And then as we move up through central London, there are many places where you see flood embankments, just as we have here, concrete walls that again protect the riparian areas from floodwater. And as we move further upstream, we also find examples of large flood relief channels. There's a large system currently in place which protects Maidenhead, and there's a very large system that's proposed to protect Oxford. However, going forward, there is now a wide recognition that we cannot rely just on these engineered solutions. For example, if we think about the estuarine areas, in places, embankments are now being allowed to fail and temporarily store floodwaters to relieve pressures elsewhere.
So if we're looking at a system like this, from my own sort of perspective as a catchment hydrologist, I'm interested in what happens during individual rain events, and we can track water through. We can track pollution that we get as a result of poor stormwater flows. We can look at the way in which water, as it passes through a city, can acquire contaminants. That might be tyre shreds, it might be microplastics, it might be hydrocarbons that can contaminate receptors downstream. There might be problems during periods of really high rain events when the sewage and the drainage system becomes overloaded, and we can have sewers that then discharge to the river. And the difficult thing with a system like this is how we take the natural system, the ways in which water passes through the catchment naturally, how we overlay that with a man-made drainage system, and how we think about that interacts with changes in rainfall, in evapotranspiration and sea level to produce a quite complicated pattern of changes in water availability and river flow spatially and temporally.
From these 3 short lectures, we have demonstrated our dependency on river-sea systems for societal well-being. Despite this, poor planning and management, coupled with the pressures of climate change, have upset the natural equilibrium, in some cases irreversibly. Effective management to preserve river-sea systems and their functioning for the benefit of all requires an approach that crosses disciplinary and geographical boundaries to ensure these environments continue to function effectively, supporting natural ecosystems whilst also providing sustainable opportunities for economic growth. This is the focus of the Pan-European Danubius research infrastructure.